this is our second lecture on the chemical vapor deposition of graphene. So what did we learn in the previous class? Briefly, we learned that number one, there can be different types of CVD reactors. Some of them have the entire CVD chamber heated and some of them have only the substrate heated. Also, the fact that the flow inside your CVD chamber must always be laminar. And we also learned that there are various parameters that influence the CVD reaction. That basically means that they influence the deposition patterns or the quality of your deposited films. Okay, fine. So now we are going to a little bit elaborate, upon those previous parameters that we have learned. One of them was the most important thing, in fact, is the fluid dynamics. How the fluid flows inside your chamber. What is the pressure inside your chamber? And how does the heated region influence the fluid flow patterns. Okay, so one very important concept in this aspect is what is known as the boundary layer. Okay, what is a boundary layer? Maybe some of you already are aware of it, but I'll briefly describe it again. When you have any fluid, let's say your CVD reactant gases flowing inside your chamber, then very close to the substrate, let's say this is your substrate, and then you have all the gases coming from here, very close to the substrate, what will happen? What will be the velocity of your gases? Zero, because you're now very close to the substrate, and on top of the substrate you're getting your solid particles deposited. So that is where you have the velocity zero. But as you move up, the velocity rapidly increases, and at some point it becomes equal to the velocity or the flow patterns inside your entire chamber. Okay, this little region where you have the fluid velocity rapidly increasing, being zero at the surface, at the substrate level. Also, it depends how large is your substrate. Is your substrate it's just one very small part of your entire tube, or if it is a long substrate throughout your tube. So depending upon all of these factors, you can define this region, which is your boundary layer. So here I will describe it with a diagram. So let's say this is your substrate, and this is L is the length along the substrate, and in that case you have this kind of velocity profile. So you know that very close to the substrate, let's say here, there your velocity is zero. Okay, and then it rapidly increases, so you see you get a profile like this, and this region, this layer, is known as the boundary layer. It is often described by delta, and this delta equals L divided by square root of your Reynolds number. So Reynolds number we also talked about in the previous lecture. Briefly, let me also mention it one more time. This is rho Vd divided by mu. So rho is the density of your fluid, V is the velocity of your fluid, D in the case of tubes, it's the diameter, otherwise it is the characteristic length that you would take, and mu is the viscosity of your fluid. Okay. Also, the other factor, the delta, is the thickness of the boundary layer. So you can see that this is very strongly influenced by the velocity of the fluid, because velocity influences the Reynolds number. And then the Reynolds number in turn influences, it is inversely proportional, the square root is inversely proportional to the delta. So basically you can now play with all these parameters in order to ensure that you have small or less thickness of the boundary layer. By the way, why do we want the thickness of the boundary layer to be less? Because this is the region where you want the diffusion of your solid particles into the substrate, right? And the boundary layer prevents or at least decreases the rate of diffusion of your solid species which were generated after the pyrolysis of hydrocarbon. This kind of prevents or reduces the rate of the diffusion, and that is why you would like to minimize the boundary layer. This is one more thing that you need to optimize in your CVD chamber. Okay, so now what are the rate limiting steps? Rate limiting steps means what slows your process down, what is the slowest step in your process. Okay, so is it always the diffusion? So since we were talking about the boundary layer, is it always the thickness of the boundary layer that would sort of that would be your rate limiting step, or can there be some other things? It turns out that it depends on your reaction. It depends whether or not, what is more important for you. For example, if there is a certain CVD process where there are complex reactions taking place inside the gaseous phase. So basically your reactants, maybe there are two gases A and B, they are forming some sort of a compound which is C, and then you're getting that C deposited onto your surface. In that case, here the reaction between A and B is very important to you. Here you need to manage, or you need to optimize the concentration of your reactants and the residence time and all of these things. So in certain cases, that process, the process in the gas phase, can be your rate limiting step. But in the other cases where the gas phase reactions are relatively simple, and they are also thermodynamically favorable at a given temperature, in that case the diffusion can become more important, and there you need to work on minimizing the boundary layer thickness, for example. Okay, so this is what I have also written here. So the first type, where I was saying that the reactions are more important, in that case what we call that those kind of reactions, we say they are reaction rate limited or reaction kinetics limited. Okay, so these kind of processes are rather common in low pressure, low temperature type of CVD reactors. And also, of course, it depends also on the nature of the CVD process. Okay, so the idea is that if for any given reason the reactions that are happening in the gas phase are not rapid enough, then in that case that is your rate limiting step. The other type, as we already discussed, is the diffusion limited. So diffusion limited would typically happen in high pressure, high temperature cases, because whenever you have a thick boundary layer, then you will have the diffusion limited process. Okay, because this is now, that is your bigger challenge. That is what you need to sort. Okay, so as I already mentioned, then you can play with some of these Reynolds number parameters. What you can also do is well, generally you would like to, you can also play with the flow rate of your gases. So if you increase the flow rate, or if you increase also sometimes the concentration, in that case if you're increasing concentration, let's say of methane, even though the boundary layer is thick, but now there are a lot of carbon species that are produced, so the concentration of carbon species increases. So even if the diffusion rate is low, whatever the total number of carbon species that are reaching your substrate can be increased. What else can you do? You can also increase the residence time of the gases. So basically that depends on your reaction. You can play with these parameters such that you can minimize the effect of the boundary layer if you cannot get rid of the boundary layer. Okay. Some little tricks also you can play. For example, this one where you just tilt your substrate a little bit. So in that case, whatever is the influence of the boundary layer, that can be minimized. So these are some other tricks. That sometimes also you can rotate your entire substrate. Then in that case you can get the film deposited uniformly on different locations. So these are some of the things that you can do for again improving the uniformity of your film. Okay, so in continuation with that, let's now summarize what are the parameters that matter to us. Okay, temperature. I have not, this temperature is very important, but I have not discussed it in great detail. And there is a reason for that. I have not given you one specific temperature for graphene CVD. The reason for that is, number one, the parameters can slightly vary. The temperature can also slightly vary depending upon your catalyst, for example. Why? Because different catalysts, different metals have different solubilities or diffusivities of carbon species. Okay, so depending upon that, you will have slightly different temperatures. You will also have different temperatures for the decomposition, the pyrolysis of different hydrocarbons. So we have mainly talked about pyrolysis of methane, but one can also use acetylene, one can also use some other, even benzene, many other hydrocarbons, even some liquid phase hydrocarbons like light alcohols and so on can be sprayed inside the CVD chamber, and you can also pyrolyze them and get some solid carbon from them. So this is something that you know, that even liquid and solid hydrocarbons are pyrolyzed for various applications, for making different types of carbons. So you can actually have variety of precursor, a variety of substrates, and also of course you can optimize all other, like pressure also you can is something that you can play with, So based on all of these factors, you can often go down, you can reduce your carbon collection temperature. Okay, typically, I would say the temperature should be above 800. Even 800 for me, I would go for 1000, for example. But in various publications, very low temperatures have been reported. So then you can look into those individual publications and also see what exactly is the morphology of the graphene that they are producing, in what quantity. So there are then different parameters. Everything becomes important there, and that's why I have mentioned the set of parameters that you can optimize. But you need to do it for your own system. And if you are trying to reproduce any method which has been previously used, then also you need to optimize. Then also you need to understand, do you have the same Reynolds number in your system that was also the in the other system, and so on. Okay, so this is the list of parameters that you need to optimize. One more thing that probably I did not discuss in detail is the defects or vacancies on your substrate. So let's say this is your, where is my substrate? Here. Okay, now there is a carbon species which falls onto it, which is actually, this is also this whether or not this carbon species stick to your substrate, with whether it is adhere to your substrate. This is defined by something known as the sticking parameter. And this sticking parameter basically tells you what is the probability of your particle sticking or adhering onto your substrate. Okay, now if your substrate has vacancies, so now let's say you have this carbon particle here, species, and then it migrates through your entire substrate. Now wherever it finds the right place to sit, if there is a vacancy, if there's a defect, that's where your carbon will go and sit. If the vacancy size or the defect size is large enough that multiple carbon atoms or species can sit there, then they will all go there, and then that will definitely nucleate something. Your film might nucleate from there. So you may or may not want that kind of behavior from your carbon species. Sometimes you just want one single extremely thin film. You don't want multiple nucleation points also. And the uniformity of the film in the single layer is more important to you, especially in the case of graphene. In that case, you can use single crystal type substrates, or you can use polycrystal, depending upon what kind of film that you're looking for, and what is your ultimate application. Sometimes, in most cases, when graphene is produced on these metal substrates, what do you do after that? You often transfer the film. So I grow the film here and I transfer it onto another substrate, and that transferring can be done simply by by adhesion and peeling off. But you can also, because often the substrates, the catalysts are transition metals, they can be etched with acids. So you can also then perform the etching processes in order to remove your graphene layers and transfer them on top of the onto another substrate that is the desirable substrate for you. Okay, and in fact a lot of research is also going towards this direction, where the removal or the pattern transfer, the graphene transfer efficiency is people are trying to improve. What do you mean by transfer efficiency? That means that you should transfer your film without any damage, or without creating any cracks or defects and so on. Okay, so these are all the important parameters that you need to work with. So now let's talk also a little bit about our very specific reaction, or reaction, the process. So what was the reaction? Again, this is the pyrolysis of a hydrocarbon. I told you that it's not just methane, you can also use various other hydrocarbons. Okay. And yeah, if you use another hydrocarbon, definitely the entire process is going to change, because even the decomposition behavior of that hydrocarbon is definitely different from that of methane. Okay, so this is one thing. One important thing again is that when your methane or any hydrocarbon for that matter is pyrolyzed, what kind of carbon species do you get in that vapor or smoke, whatever you want to call it? So people have done a lot of work in this direction. In fact, it has been also very interesting, not just for the CVD reasons or for depositing films, but also because we know, when in this entire course that we have discussed, that there are certain types of carbon materials that are still very intriguing for scientists, and we are still trying to figure out, oh, why doesn't C2 molecule exist? Does it exist? And if it does, then how short, is it metastable? Is it very short-lived? And these kind of molecules between C2 and C8 have been here and there seen in these kind of what is known as carbon vapors. Okay, people have also observed the presence of carbines. These are the linear chain-like molecules, we discussed that, which have sp hybridization. So whether or not they exist also people have been debating, and there has been also a lot of work where people have experimentally observed carbines. So these kind of the pyrolysis of methane or whatever is the product of your CVD, that is also very interesting for people to understand what kind of carbon species are generated in these systems. So one, it is not right to think that the only carbon species that you're going to get is atomic carbon. Now, often you would hear about atomic deposition of carbon, that is how graphene is generated, or any carbon material for that matter. Well, atomic deposition, of course, there are very small carbon species that are depositing on top of each other, but we don't have only carbon atoms or carbon radicals inside the system. That is something you must understand. You also should understand that methane at higher temperatures becomes less stable compared to benzene. So again, in the lecture where we talked about the pyrolysis of methane, then you remember that benzene, naphthalene, other aromatic compounds become more stable than graphene because their enthalpy is then less positive compared to methane at higher temperatures. So I think above 800 or something like that. So at those temperatures, then you will also find some cyclization in whatever is being produced, from your methane pyrolysis. So that is why you will have a mix of all of these things inside your CVD chamber. It's not necessarily just solid carbon particles in there, atomic carbon particles and so on. Okay, fine. So yeah, there are various things that you can also then just learn about the methane pyrolysis or stability of various hydrocarbons, and then you will enthalpies of formation of various hydrocarbons. Okay, catalysts, that's the third important thing for us, that generally transition metal catalysts, we can also use carbon itself as the substrate that we have discussed before, but there are various metals again that have been tried, copper and nickel being the most common ones. And copper nickel, there is a reason. People have been studying carbon deposition on nickel for a very long time, and nickel seems to be a rather suitable metal that so there are also then mechanisms proposed. So for example, in the case of nickel, it is believed that carbon particles do go inside the surface a little bit and then they are precipitated out. If you can relate this to the formation of quiche graphite also, that's an interesting comparison, because also in the case of quiche graphite, what is happening is you have carbon precipitating out of steel when you perform the rapid cooling. So these are also, there is a precipitation of carbon, atomic carbon, from inside a metal. So in this particular case also, there may be carbon species, again not necessarily atoms, that go inside the nickel and then they are precipitated out. In the case of copper, it is believed that the reaction is more of a surface reaction, and that is indeed also the reason copper gives you thinner films, and that's why for when you want to make fuel layer graphene, often people rather select copper substrates. But various metals may have slight variations also when it comes to the mechanism of formation of carbon sheets. Okay. So what else? We also need to discuss again a little bit about the solubility of carbon. So I just mentioned to you that the nickel, the carbon particles or carbon species can go inside nickel and come out. This is what you know as the solubility. The diffusivity, another property. Diffusivity tells you how much how easily can carbon diffuse inside your metal. Okay, so these two properties become very important. Here I have again pasted these curves that I had shown you in the methane pyrolysis lecture. These are the solubility curves. Carbon solubility in gas phase. This is more or less a pattern that you see. Then of course, for different metals, for different temperatures, these curves will vary. They will shift here and there. But this is sort of the profile. This is what you see. what you see, an important thing is that as you change the pressure, how these curves change. And what is this minima, where you see the minima in this curve? For different pressures, again, you see the different values of minima, that is your temperature value. That minima for your specific curve is the best deposition or collection temperature. Okay, C by H here is the ratio of carbon to hydrogen. Okay. Fine, so solubility is important to us, diffusivity is important to us. How can you work with these parameters? You can optimize the deposition temperature according to these kind of curves. Okay, and you can work with the pressure, of course, and then the minima can also shift slightly. Then you can also control the morphology of your film. The film also, the morphology of your substrate film. And that will also make a difference to your solubility. Okay, so these are some values I have taken from this publication. 750 degree centigrade. These are the range for nickel and palladium. You find 10 power minus 9 centimeters square per second. That is the range where you have the solubility. For different metals, it differs, and you can actually have a look at that publication, and then you will find some of these values. I'm sure there are also many more resources where you can find the solubility values for carbon in different metals. Okay, so altogether now we will be discussing about CVD also in the context of carbon nanotube, nanofiber, different nanomaterials. Okay, because CVD has also somehow become, it used to be just a film deposition technique. And even in the context of graphene, we are making films, so we can still call it a film deposition technique. For some other carbon materials, for example, diamond-like carbon, also you use CVD for film deposition. However, CVD also can be used for growing or manufacturing other carbon nanostructures such as nanotubes or nanofibers, also vapor-grown carbon fibers and so on. So this is also something we are going to discuss again. So we will be again coming back to CVD. Okay, but what are the open questions? In general, this is not just valid for this particular lecture, but in general, what are the questions? Why CVD parameters are still being optimized, and what are the things that will help you optimize your process, or that will help you increase the yield and get better quality films? Okay. What are the limitations that you can overcome? So for example, boundary layer, that makes a lot of difference, and that influences the diffusion. So what can you do to your substrate to overcome the boundary layer? Can you, for example, perform some microfabrication, some sort of patterning of the substrate that can actually help you overcome the boundary layer conditions? Can you somehow change the flow of the your entire system very close to your substrate by just designing your substrate in such a way, maybe complex geometries, and then overcome the effect of the boundary layer? So that is something maybe you can do, because we just saw that you can tilt the substrate and that helps. So just, can you do something more than just tilting? Okay, can you also, there is when it comes to the mechanism, there is also one interesting question. What should be, when we talk about the solubility of carbon into these metals, these are solid solutions. We are not talking about liquid solution, we are still talking about solid solutions. But there are certain cases where especially when you use copper catalyst, then the temperature of your CVD process or the substrate is pretty much almost equal to the melting point or just below the melting point. So is that process different from what you would have in not liquid, completely solid, or if your CVD temperature is way lower than your melting point? In that case, is there any difference? So that's also one interesting question that can tell us about the mechanism of CVD. Okay. Yeah, another thing is that what is happening in the gas phase and what is happening on top of the catalyst. So this is something, if we know it, then we know a lot about the mechanism of the CVD process. This problem can be addressed. So if you know what are the byproducts of your methane pyrolysis, then you already know what are the things that are happening in the gas phase. That much you know. So you can just collect your exhaust from the CVD. Maybe don't have any substrate, just collect the exhaust. You can have the hot wall reactor. and then you can analyze the exhaust, and sometimes even you will have the tar deposited here and there. So if there is some sort of tar in any furnace where you're processing hydrocarbons, that means there are some light hydrocarbons there, but they were light, but they were not so volatile, they could not go away. So those tars are valuable, collect them and analyze them. So that can also help you understand what is happening in the gas phase, and then, well, what is happening also on your substrate. If you can analyze it using some in situ methods, that will address a lot of questions. So with these questions, I will leave you here. There are various NPTEL lectures on the chemical vapor deposition process itself, and there are many parameters that I have not covered. Also, not just chemical, but also physical vapor deposition and plasma enhanced. And there are various methods of various vapor deposition techniques, and some of these lectures cover those, the entire range of vapor deposition techniques. So that is something I recommend that you read. At the end, I have also, in the beginning, I have mentioned this handbook of CVD. That is also very useful, and I was able to get some information from there. Of course, you can also find your own resources.